Spectroscopy is a huge technique, huge in the sense that there's lots and lots of spectroscopies out there. And the thing about spectroscopy is that, or organic chemistry, I should say, is that it is not complete without spectroscopy. Okay, so you have to do some analysis on your compound. So the analysis you may have done in your lab so far may have been things like melting point or boiling point. And I know some of you have also done IR at Capital because they do that in organic one. We do it also in organic one. We just do it a little later. But, so analysis is an important part of organic compounds. Otherwise, when you do a synthesis and you form a compound, then how do you know what you have formed? And can you, 100% say with a guarantee that, yeah, this is what I was proposing to form, and now I formed this. So you need to be able to prove, okay, to people. So depending on where you want to publish your data, where you want to publish your paper, your research, those journals will give you a little bit of a guideline that, okay, we need this and this and this before we can publish your paper. Otherwise, yeah, we can't take it. All right. So which means that good data is a really important thing for any kind of science anyway. Spectroscopy is different kinds of spectroscopies. Okay. So I don't know what the next one is. So usually every department is going to have some sort of instrumentation. The funny thing is, in organic chemistry, like even in our lab, we do melting points all the time for analysis. But the thing is, melting point is not even like, required in some cases for showing your data. So you can do the melting point just to have a data point, but it is not that kind of an analytical technique that you can use it to publish data. So it's like, it's not even there. So you learn all these things about melting point, and yet we don't really get to use it. But anyhow, so it's an analytical technique which helps you determine the structure. Each technique will do different things, okay, that, that is required of that spectroscopy. And then depending on the technique that you're using, you will either have your sample or you will not have your sample at the end of the technique. So I will go through that also as we are learning through all of these spectroscopies, okay? So depending on what you're doing, here is the different kinds of techniques that you can use. So UV-Vis spectroscopy, ultraviolet spectroscopy, it actually also includes the visible spectrum in there. We have infrared spectroscopy, mass spectroscopy, and then nuclear magnetic resonance. That's also a spectroscopy. We're going to do all four of them, okay, over here. UV and MS, they're kind of going to be little tiny for us. Infrared is going to be a little bit more detailed because it's used a lot more, at least in the teaching labs. And depending on what you're doing, as far as your research is concerned, you may be actually doing a lot more of IR. For me, like when I was doing my research, I did not even touch the IR. I didn't have nothing to do with the IR. Everything for me was ultraviolet spectroscopy and mass spec and NMR, so it depends on what kind of research you're doing. You may completely not do one or the other, but mass spec and NMR is something that every chemist will do, okay? One way or another, you are going to have to do that. So these are the four spectroscopies that we cover generally in undergrad. It doesn't mean this is the only thing. There is more. And depending on your research lab, as I said, you could be doing more techniques in there. You might have very custom-made instruments. Some professors do that. They're very good at making things, and they make their own instruments. So before we go into UV-Vis spectroscopy, I want to just introduce you to the electromagnetic spectrum. So I do this usually before IR also, but now that we're doing it now, I will not have to do it then. So electromagnetic spectrum is, of course, the most important thing when we are talking about spectroscopies, because we use a lot of these regions. So you must have seen this before, the electromagnetic spectrum, maybe in Gen Chem 1, because technically we are supposed to be talking about the electromagnetic spectrum because the electronic structure, okay, it's part of that. But anyhow, so the electromagnetic spectrum is composed of different kinds of radiations. Now, we didn't create those radiations. They're all coming from cosmic radiations when they hit the atmosphere, they kind of spread out just like a rainbow does, right? So in the rainbow, you can see all of these different colors. With the visible, so here's the rainbow, okay, right in the middle, the green one is the rainbow, but everything else is not visible to the naked eye, you know, so we can't see it. You can feel some of it, but you can't see all that radiation. There are a couple things that are really important in this slide that I would like you to kind of understand and know, because once you know that, everything else is going to be easy. Okay, so first of all, it is this equation that you need to know. The speed of light is equal to the wavelength multiplied by the frequency. Remember, speed of light is a constant, okay? 3.0 times 10 to the power 8, I think, kilometers per second or something. So that is the constant. The speed of light is constant, which means you can change the frequency, you can change the wavelength, which they do change, okay? Depending on what kind of radiation you're looking at, those things will change, but the speed of light does not change, okay, for us. The other thing that is really important for us to know is the second point here, which is that frequency and wavelength are inversely proportional. So the way we write that is that lambda is inversely proportional to frequency. Lambda is the wavelength, and nu, this is nu. I think I've drawn that before when we were talking about radiation. So that is nu, and nu is frequency. So lambda, which is the wavelength, is generally given in meters or nanometers because that's the length unit. Frequency is generally given in hertz, and in some cases, it's given in some other units also, which we will talk about when we get there. So that's an important thing to know, okay, that the wavelength and frequency are inversely proportional. The other thing, and by the way, that's written right here, okay, on this slide. So you will never forget this. So higher frequency, shorter wavelength, okay, because they're going in opposite directions. Now, the other one that I need you to know, the other equation that is kind of important for us is the energy per photon. This is the third equation here, or the fourth point here. This is E is equal to h nu. And I think this is what I mentioned to you when I was talking about nu, and when we write that in the free radical reactions. So energy is equal to h nu, where h is the Planck's constant. Okay, so energy is actually directly proportional to frequency. The amount of energy given by the radiation, that's what we're talking about, is directly proportional to the frequency. To remove the proportionality sign, you have to add a constant, right? So the constant here is h. Okay, it's not a math class. Let me get out of my math mode here. But in any case, so E is directly proportional to nu, which is frequency. So higher frequency means higher energy. So if you note here, again, let me show you the higher frequency is equal to higher energy. Okay, so that's the purple thing that I have circled there for you. So, and that's an easy one to remember. When you have direct relationships, they're easier. The opposite ones, the inverse ones, are sometimes a little harder, not harder, but, you know, I mean, it's easier to remember direct ones. Okay, you know, if this increases, this also increases. So frequency increases, energy also increases. Okay, so these are some of the basics that we have in an electromagnetic wave kind of thing. Okay, because I haven't even talked about the spectrum yet. We're just talking kind of about the wave. All right, so the wavelength is one big crest, so going up and then going down. So that is a crest, that's a wavelength. And the number of waves passing through 1 second, that's frequency. Okay, so there are two different things. The wavelength is from one starting point of a crest to the other point of the crest where it finishes, one big cycle. And the number of cycles per second, that's the frequency. Okay, so now you know the relationship between the two, and you know the relationship to energy also. Okay, all of these things are important here for us to understand the electromagnetic spectrum. First, tell me if you have any questions about any of this. Okay, And the reason I'm saying also because later on when we talk about that, oh, look, the frequency is increasing here, I want you to be able to make all the other connections there as well, okay, that go with frequency, that go with wavelength, because in any kind of the spectrum that we talk about, we say, oh, okay, look, this is absorbing at a higher wavelength. If it's a higher wavelength, larger wavelength means low energy, okay? Because larger wavelength means that it's a lower frequency, okay? Because wavelength and frequency is inverse, okay? So let me leave that there because it's inverse. So when you have a large wavelength, you have a small frequency. Small frequency means small energy, okay? So it's not that much. Anyway, so you have to make those connections when we look at a spectrum, and then we look at the scales, okay, on all of those. Okay. Now I want you to understand the electromagnetic spectrum a little bit. I'm not saying you should memorize it, but I am kind of hinting that you should know it, okay, for sure. And I think it will not be that hard for you to know it because you've heard of all of these radiations. So the first radiation that was discovered was actually the radio waves, okay? And this was discovered by Marconi. And I shouldn't say discovered, should I say discovered? Yeah, discovered. He was the first one to actually use radio waves as a form of communication. Okay, the rest of the waves were not even used at that point. So radio waves were the first one. And then you can look here at the wavelength, and the scale here is centimeter. So it is a pretty high wavelength, okay, over here. So large wavelength. So radio waves are actually pretty harmless because they have such a large wavelength. Their energy is very low. Nobody died of listening to a radio, okay? So it's not going to happen. Radio waves will never kill anybody because they don't have that much energy, okay, to kill anyone. So in any case, that's radio waves, okay? And radio waves, as I said, were the first one to be used because of their large wavelength, and people could kind of, trap them. And the next one is microwave. I'm not saying that that was discovered next. I'm just saying that the next in line is microwave. Why so? Because they are a shorter wavelength, and now the energy level is increasing. So as you're going higher and higher, the energy level is increasing, which means the frequency is also increasing, okay, as you go from radio waves all the way to gamma rays. I'm going to take you through all of these, okay? Radio waves we are going to use when we do NMR spectroscopy. Okay, that's where the radio waves are used because you need a very small amount of energy for radio waves. Microwaves are not used in spectroscopy. Microwave in chemistry is used usually for synthesis, so or doing chemical reactions. So instead of using heat or Bunsen burners for chemical reactions, you can use a microwave, just like we now use microwave for cooking. And oh my God, did that change the world or what? So now we can cook, almost anything in a microwave. And so similarly in a lab also, okay, that you can actually do reactions in a microwave. Of course, you don't want to heat your food in that after that. After the microwave is infrared. And by the way, if anybody tells you that microwaves cause cancer, don't listen to them, okay? That's kind of all, I think it's just nonsense. You're not going to stick your head in the microwave and turn it on, I mean, that's not going to happen. So unless you're really kind of leaning on the microwave and you're getting that close to any microwaves, you'll be just fine, okay? So if you're heating your food for 10 minutes, don't be standing there and looking at it for 10 minutes. Just walk away and come back, okay, when it beeps. So microwaves never killed anybody. Infrared never killed anybody either. And infrared is above microwave. Infrared is something that we will do, okay, because as I said, this introduction is coming from my infrared PowerPoint. But infrared spectroscopy is extremely common. And as you all have said to me also in class, you have used it, okay, a little bit. So you kind of know just a general idea about, what infrared is. But infrared is actually electromagnetic spectrum. It's part of radiation, and some molecules, they can show certain characteristics, when you have infrared radiation pass through them. That's what you do. So you expose them to the radiation and they start behaving differently. So then you look at the spectrum and then you figure things out. Okay, so that's infrared. Infrared is also used somewhat in our lives. We don't use it that much, but Army does. For example, they use it for night vision goggles and all that, but infrared is the one that actually causes heat. So from the sun, when you're outside, you will actually feel the heat of the sun, and that's a lot of it is just infrared radiation. There is all sorts of radiation in the world, by the way. Okay, in our environment, there is all sorts of radiation. So you're getting exposed all the time to radiation, one way or another. You have no chance of escaping that. Okay, so it's just a matter of what level is your exposure. So in Florida, for example, if we are out in the sun for too long, of course, we'll get a lot more radiation from infrared, visible, and ultraviolet. Even sometimes in sunny days, the radiation comes through the clouds. Okay, so it can travel through a lot of things. Okay, so then comes the visible radiation. Now, visible is, of course, something that we can see. Visible is actually a very tiny, tiny sliver of these whole electromagnetic spectrum. But my God, thank God it's there, because that way we can see color in everything, So we have the VIBGYOR or the Roig-Biv, however you want to remember your rainbow colors. Those are all there. And of course, today we will do visible spectroscopy. The nice thing about visible spectroscopy is that you use it only for compounds that have color. Obviously, anything that is colorless is not going to show up on a visible spectroscopy. So that's why it's kind of fun to work with, because you're working with colored compounds then, you're not working with colorless solutions all the time. So visible spectroscopy now, or visible radiation, has a little bit higher energy than infrared. Okay. When we go through all these spectroscopies, my goal is to tell you the theory about what's happening, okay? Not just how to interpret the spectrum, but how do you actually get that spectrum, okay? Not the instrumentation. That's definitely not my forte. I cannot tell you how to design an instrument. I'm just happy I can change a bulb in my home. That's kind of my limitations that I have for doing any kind of, technical work. But I will teach you the theoretical aspect of how these techniques are working. So visible, when we do that today, I will tell you how that's working. So then you get to UV radiation. Now, UV radiation, depending on which kind of electromagnetic spectrum you're looking at, it'll divide it into different sections. And by the way, the electromagnetic spectrum, all of these divisions, these are all made by scientists, in the sense that nobody told us. It is not written in anywhere God's book, that this is going to be called gamma rays or this is going to be called visible radiation. No, the scientists decided, okay, we're going to chop, this electromagnetic spectrum. And from here to here, we're going to call it infrared. From here to here, we're going to call it microwave, So, I mean, this is all a design of the scientist, okay? And that's why sometimes when you look at the UV radiation, they divide it in different ways. This is divided into near and vacuum. Another place they might say this is UVA, UVB, UVC. So it depends, okay, on which book you're looking at, or where you're looking at for the electromagnetic spectrum. It doesn't really matter to me. I don't divide it. We'll just call it UV. And so after visible is ultraviolet radiation. Now we're getting into really high energy zone, and UV radiation starts getting dangerous for us. Visible radiation doesn't kill us either, unless you're wearing hot pink, then it's like, okay, I think my eyes are hurting now. But other than that, visible radiation is not going to hurt you, okay? But ultraviolet now can actually cause problems. And again, little bit of it is not bad. But the more exposure you get to ultraviolet, the more you have the chances of getting cancer or any kind of skin disease. Because again, remember, we've talked about this before, that your organ, the biggest organ in your body is your skin. And we talked about the fatty acids that you need in order to protect. And we talked about how the skin is made, not skin, but really the cells. They're the bilipid layers and all that. So the vacuum, the ultraviolet radiation here can actually break those bonds, okay? The double bonds that we have in our bilipid layer, it can break those. And that's why sometimes people who are really out there in the sun all the time, their skin, you can tell when somebody has been outside a lot, because they wrinkle faster, or their skin is a little bit damaged, or they have sunspots, all of those kind of things happen. And some people are prone to a little bit more damage than others, and so some some of us, like, Indians, for example, for us, we have melanin in our body, which protects our skin a little bit. So it depends, from which race you are. You may have certain pigments in your body that can protect you, and sometimes we don't. And so you have to protect your skin, okay, in different ways. And just because I have melanin, it doesn't mean that I can't get skin cancer. I can still get that. So I still have to protect my skin. Anyway, that's ultraviolet radiation, because now you're getting into a higher energy level. Okay, so it's damaging to you. X-rays are higher. Now, X-rays and gamma rays, you will generally not find that in the atmosphere. Okay, so our ozone layer, which also we have talked about back in Organic 1, our ozone layer actually protects us. It protects us from UV radiation also. And that's why it was really bad that the ozone layer had a hole in it, because a lot of the ultraviolet radiation was coming through. And the more radiation comes through, of course, the more diseases we will get, because there's more energy in the system. So, but gamma rays and X-rays definitely are not going to be around that much. Okay, so you don't get exposed to gamma rays and X-rays unless you are deliberately exposed. So, for example, if you go for an X-ray, okay, whether it's a dental thing or whether it's a broken bone or something like that, then you will get exposure to X-ray. And X-rays are, you can see, they're so high energy that they will go through you. Okay, the ultraviolet radiation gets absorbed in the skin, so it's getting through your skin, but X-rays will actually go through your whole body, so you can see how damaging that can be, because they are so high energy. And generally, doctors will recommend, anybody will recommend that you have only one X-ray per year. And so, I feel bad for some athletes, because if they get injured, they have to get more X-rays, and they're just exposing themselves to more radiation, just because of their profession. But, X-rays are very damaging. Even the nurse is going to leave you in the room, by yourself, while, she takes the X-ray or he takes the X-ray. So it's like, it's bad for you. And they cover you with lead. The other parts of your body are covered with lead, because X-rays don't penetrate lead. So then only the part that, that the X-ray is needed off is going to be exposed. But anyhow, very damaging. X-ray machines are very common, though. You can find them everywhere. All doctors' offices, dentist offices, they have them. You can find X-rays, of course, in all departments. A lot of chemistry departments will have X-rays, because we take X-rays of all our molecules. So X-ray spectroscopy is also a technique. We don't do it because it's a little bit higher. I don't know, not everybody gets to do X-rays, not all molecules require X-ray spectroscopy. So depending on your work, you may or may not do X-rays, so, but anyway, it's everybody, X-rays are not that hard, okay, to make. So you still need a radioactive compound, but it's easier to get X-rays. Gamma rays, on the other hand, are a little bit harder, because now you're getting to really, really high energy levels. And gamma rays can really be damaging. If you don't know what you're doing, then gamma rays are really, really damaging. And so the only place where you find gamma rays at this point, and I hope you don't have to, even know where they are, but they usually find them in the cancer hospitals, because you get gamma rays treatment. Okay, so that's the radiation treatment that you get. And actually, they will not even send you home. So anybody who is getting a radiation treatment, they generally will stay in the hospital for 2-3 days. Not, and they say that we're glowing, but it's, it is radioactive. And of course, you get radiation. So they want all the radiation to be gone before you go home and all that kind of thing. So gamma radiation is really, really bad. Now, we don't use gamma rays for any kind of spectroscopy. Okay, so let me tell you what we will be using for spectroscopy, because those are the ones you will hear me saying again and again. So we will be talking about radio waves in NMR. We will do infrared next week. We will do visible today. Actually, we will do UV vis today. They go together, okay? So we will do that. Mass spec, MS, I will just write that. Mass spec is not part of the electromagnetic radiation, because it works in a very different kind of way, okay? So that is your electromagnetic spectrum. I hope the way that I have explained it to you will help you remember all the energy levels also, okay, for it. Otherwise, you can take a look at this diagram and hopefully that will help you, because one of the questions sometimes I do ask is, you know, you have all these radiation, which one has higher energy than the other? Okay, so those kind of things. Any question in this? Okay. So now we'll get to start with the UV vis spectroscopy. There we go. So UV vis spectroscopy is, of course, the ultraviolet and visible spectroscopy. And this one here, I think, let me see where I have that. I don't even have that. Yeah, it's really not a very well made PowerPoint because I don't teach it that often. But ultraviolet spectroscopy is, of course, based on the visible region and the ultraviolet. So if you remember, they're kind of right next to each other. So what happens is any kind of spectroscopy, and let me see, I know I have a schematic here somewhere because I want to show you that first. There. So the schematic will kind of give you an idea of what I'm talking about. And maybe you've seen this in the lab already. Okay, it's possible you have. So generally a UV vis spectroscope will be a very small instrument. It's kind of like a desktop, you know, so you have a small case, you know, where you put your sample in and then you have a screen and that's it. Really, you don't need a whole lot of things. So as I said, a desktop. So you have a desktop computer and a screen. The insides of the UV vis spectrophotometer, of course, are the interesting thing because you need a source, okay? For any kind of spectroscopy, you need a source, and a source is going to be for the energy. The energy source is the big thing here because you want to get in the right range. You want to get the wavelength, the energy in the correct range. So in the ultraviolet spectroscopy, or UV vis spectroscopy, you need the range in which you have the ultraviolet radiation and the visible radiation. So that is going to be your source, okay? Then you have to keep your sample somewhere. So your sample that you're keeping there, you keep two samples, okay? So one is the sample itself, which here right now is dissolved in solvent, and we'll talk about that. And the other one is called the reference self, and that is just with the solvent, no sample. Because what you need to do is you need to nullify the solvent itself. So when you pass the radiation through, you will only take the spectrum of your sample. You don't care about the solvent. So that's why you have to take the spectra for the solvent itself. So in any case, so you have these two beams that come through, and then you have the detector. So the source is an important thing, of course. The detector is the other key thing. If these two things are not correct, then your spectrum is your spectrophotometer is not going to work. The detector will detect. And how does it detect? Again, that's what I was saying, the technical aspects of it. I remember doing a course in spectroscopy and we learned about it back when, but we don't need it anymore. So I don't remember it anymore. And so, you know, just like, you know, if you don't use it, you kind of lose it. And that's what happened to me. So I've lost how we make a detector, or what are we detecting in here, you know? And so anyway, but you do need a detector, okay, in order to give you your output. As an organic chemist, I will tell you the one thing, and I'll be very honest to you about this, okay? I've no shame, I guess, in saying this. For me, when I look at an instrument, whatever is inside the instrument, that's fine, that's great. Kudos to you that you made it. But for me, please show me where I can press the button that says start scan, and then I can press that button and I can get a scan, and then I can walk away with my spectrum and just leave me to the analysis. You know, that's it. How you make the instrument is entirely up to you. I just want to get my spectrum. That's it. You know, I mean, that's kind of has been my thing. And, you know, some people are more towards making the instrument. I am more towards using the instrument. So I'm a user. Anyhow, so then after the detection, you get your spectrum. Once you get your spectrum, of course, you know, you can manipulate that using the computer software. print it out, do whatever you want. Okay, so this is your basically your instrument, okay, for UV vis spectroscopy. The good thing about the UV vis spectroscopy is that it is very affordable to do. So you can get a nice UV vis spectrophotometer for about, you know, anywhere from $20,000 to $30,000, which I know it's a lot. It's a lot for us as personal, but for a department, you know, they can find the money, you know, to buy an instrument. So I personally would not buy it. I don't have that kind of money, but, you know, departments will be able to. But it's a very affordable technique, you know, to use in a lab. It has its function. Everything has its function. Okay, so let me talk about a few things here before I move on from this. And the main thing I want to talk about here is the sample preparation. So in this case, the sample is taken, whatever you have, liquid or solid, doesn't matter what kind of sample you have to dissolve it in a solvent. Okay, there is no way that you can use this spectroscopy without dissolving your sample in a solvent. So you have to dissolve it. Now, generally what happens is that your solvent that you get is called spectrophotometer grade. And what that generally means is that you don't really need a reference cell, okay, which means the reference cell with the solvent. So if it's a spectrophotometer grade or UV vis spectrophotometer grade, it means that whoever has made the solvent, the company that was making the solvent, has taken out anything in there that could absorb light, okay? So it depends, okay? But if you are not sure, then definitely keep a solvent as your reference cell, all right? So you need to dissolve your sample in a solvent. What kind of solvent do you use? Generally for organic chemists, it's going to be dichloromethane or methanol or ethanol. For a lot of biochemists, they end up using water because, you know, all their samples are soluble in water. Biochemists also don't use visible spectroscopy that much because all of their samples are colorless. So they use a little bit more of the ultraviolet radiation, okay? A lot of organic chemists can also use the ultraviolet, but usually you use visible spectrophotometer and generally you have colored compounds then, you know, so that kind of goes hand in hand. Okay, you can get your sample back if you want to, and I've written that at the end over here, is if you want at the end, you can get your sample back, just evaporate the solvent. So for me, whenever I did my UV vis, I would never, ever, ever throw away my sample, okay? Because there's, you know, the research you do, it depends on, you know, what kind of compounds you're using. Mine were expensive and I could not afford to throw any bit of my product. So I had to keep everything. So after running this, I you know, get my evaporate the solvent, get my sample back. So that is about the sample preparation. Now, about the spectrum. What kind of spectrum do you get? So this is the spectrum that you get from UV vis, and I will tell you about why we're getting this in just a second, okay? Because you need to first have an idea of what the spectra looks like, okay? So the spectrum of a UV vis is actually not all that fancy, and that's why people don't use UV vis that much, okay? Because look at the spectrum. All you're seeing is like a mountain. That's it. You know, it doesn't tell you anything. Well, it does tell you something. For people who are looking for something, they will find it, you know, but for most people, it's like, what do I do with this? You know, I mean, it doesn't tell me a whole lot, but I want to tell you some things about this before I explain the theory aspect about how UV vis works. So look at the scales. So here you have on the y-axis the absorbance. The absorbance actually goes from 0 to 10. That is about how much the substance is absorbing the energy, okay? On the x-axis here, you can see that this is the lambda. Lambda is the wavelength. Remember, the higher the wavelength, the lower the energy. So this is high energy on this side because that's the lower wavelength. And on the right-hand side, where you're getting to a higher lambda, you have lower energy at that point. So the UV vis region generally starts from 200 nanometers and goes all the way And depending on your instrument, okay, so if you invest a little bit more, you can go up to near IR, which is then 1000 nanometers, okay? Generally, you go from about 200 nanometers to about 800 nanometers. That's the general range for an ultraviolet. So here, or ultraviolet and visible spectrophotometer. Here, this is going from 200 to 350. 200 to 400 is just the ultraviolet radiation. That's it. After 400 is when the visible region starts. Okay, so hopefully you're noting all of this, okay, because this tells you where you're looking for things. The 200 to 400 is the ultraviolet radiation, which means that anything that has color is not going to absorb here. Only above 400 is where the visible radiation is where you're going to see any kind of colored compounds. Okay, so before that, you're not seeing any colored compounds at all. Things are colorless. So which means that if you're looking at how your molecule behaves in ultraviolet radiation, you look at the 200 to 400 zone. Okay, that's what you do. A lot of the biochemists will actually look in this region. All right, so, and I don't know what they're looking for. I remember, like, when I was doing my PhD and even my postdoc and whatnot, and I was working with the UV-Vis, since it was such an unpopular instrument because nobody else was working with colored compounds, our group was pretty much the only one. I had the UV-Vis to myself all the time, and that's such a luxury, to have an instrument just for yourself. So I had it to myself all the time, and the only time I had to share it with anybody was the biochemistry group. And whenever they had to use the instrument, I thought they were encroaching on my stuff. I'm like, just go away. And so I used to talk to them a little bit, of course, to figure out what they were doing, but I completely forgot now. But biochemists use more of the ultraviolet region, and they're looking at their proteins in that region. Okay, so most of the organic chemists, they're looking at colored compounds. What you're seeing right now is the UV-Vis spectrum of the isoprene unit. Remember, we talked about that a little bit. And so that's a 5-carbon unit. It has 2 double bonds in here. And so this is the kind of spectrum you get. Most of the compounds are going to have different spectrum, okay, one way or another. Right now, you're seeing only one peak, okay, in this one, but it doesn't mean that you're always going to see only one peak. Depending on your compound, you can actually have 2 peaks in there. So maybe it looks like this, and so you have 2 peaks like this. It's possible, or maybe they are far apart. It depends. So if you're looking at 400 to 800, maybe this is what you're getting, or maybe you have another peak here, who knows? Okay, so it's different kinds. So each of the top of this peak is called lambda max. Okay, lambda is the wavelength and max is the maximum wavelength it has reached. Now, it doesn't have to be that the first one is the tallest one. It could be that the first is small and then you have the large one. It could be anything. So this top part here, that's called the lambda max, which you see here also. Okay, so lambda max is the highest peak that you get. So the wavelength you note down, and this is something you can do on the computer. Okay, so you don't have to start reading like, where is my lambda max? So for example, here, the lambda max 222, you don't have to read this. You just bring your cursor over here and then it will label it for you. And so then, you're all set that it's 222 or 223, maybe just like 1 nanometer here and there, and it's all fine. Okay, so the lambda max, okay, this is an important thing, all right, because this is what is going to characterize your compound. So this absorbance is actually given by what we call Beer's law, which has nothing to do with drinking beer. This is Beer, scientist. He came up with this law. So absorbance, A is absorbance, E, C, L. So A is absorbance. I think I've given it all here. And then E, this is not E really, this is epsilon. And epsilon is molar absorptivity, extinction coefficient. So you have to calculate this actually. So there is no other way to figure out epsilon unless you calculate it. C is the concentration, and then L is the length of the light path. And let me explain the light path to you. So in the previous slide, I was telling you where you keep your sample. Okay, and so how you keep your sample is also important. So your sample is generally kept in what we call a cuvette. Okay, so it's kind of like this. And the length of this is standardized, which means the space here for keeping the sample is also standardized, and it is standardized to 1 centimeter length. This is 1 centimeter wide also. So it's all equal all around. So it's 1 centimeter. So the length is always going to be 1 centimeter, okay, in this. So this is called a cuvette. I don't know if I wrote that somewhere. No, I don't think I did. You can keep it in a test tube also, okay? If your test tube is 1 centimeter wide, that's fine. If it fits in the sample holder, that's fine. So that is the length, okay? So that's the length of the sample. Now, why is the length of the sample important? So let me give you a context over here. So if you've ever been to the ocean, and I really hope you have at some point or another, otherwise come visit me in Florida and I'll take you to the beach. So if you ever go to the ocean, or if you go to the Great Lakes, there are a lot of lakes around Ohio also. If you go to the lakes or the ocean and you look out, you will see that the ocean or the lake has different shades, okay? It's not all the same color. It can be the same color depending on where you're looking from, okay? But a lot of times you actually see different shades of blue or a little bit of green. And that is because of how much light is passing through that water. If it is deeper water, the color will change. If it is shallow water, the color will change. All right, so that has to do with how much light is passing through. And that is why this length is really important, because how much light is passing through will tell you how much of energy is also being absorbed there. Because if there is more samples in there, if there's more compounds in that region, you will have more absorption. Okay, so your color will change at that point. In a scientific experiment, you have to be consistent, that's all. So you can take a 2 centimeter cuvette, we don't care, it doesn't matter. You just have to have that in your calculation. Okay, that's all that matters. So what the epsilon really is, I've explained everything to you, right? Absorbance is actually this, right? This scale. So this absorbance right here is 0.8. Okay, so this is 0.8 right now. So which means absorbance is 0.8. Epsilon, you have to cancel. Let's say the concentration was 0.1 molar solution that you made. And you have to do this. You have to calculate all that. You have to make the solution in a proper concentration. And the length is 1 centimeter. So then you calculate the epsilon. But what the heck is epsilon anyway? What is it? Epsilon is actually the area under the graph. Okay, so how much energy is being absorbed is given by epsilon. So if you have epsilon as a high number, that means you're absorbing a lot of energy in that region. So as I said, if you have 2 peaks, then this epsilon is going to be much higher than the other one on the right side because of the small absorbance, okay, in that region. Okay, so that's fine. I have more absorbance, let's say at 222 versus 400, I don't know, whatever. So I have more absorbance at 222 versus 400. So what does that tell me then? What does it mean that I have more absorbance? It means that your molecule has something in there that is absorbing more at 222 and less at 400. Remember, 400 is lower in energy, 222 is higher in energy. So it means that you need a lot more energy to get that absorption there. Okay, and I haven't even told you how you get the absorption yet. Okay, so I'm just telling you what the spectrum looks like. But anyway, this is what the spectrum looks like. That's what the epsilon tells you. That's what the concentration tells you. Will you have to use the Beer's law for me? You will not have to use it. So I just need you to know that we follow this. And each of these things are important for us. Okay, in a calculation, absorbance, length of the absorption, and concentration, everything is important. Okay. So this is your UV spectrum, okay, and what it might look like. Any questions so far? I know I've been talking for about an hour now. Okay. Okay, so this is the graph, all right? And now let's talk about why you get the graph, okay? So that's the important part. The graph is fine and all that kind of stuff, but the theory behind it as to why you're actually getting this spectrum, okay? That's the important part, and that is given right here. All the other things here, these are just to tell you all the absorptions, okay? So this is where we started. The next one was showing you this absorption, okay? So this actually tells you that the more conjugation you have, look at this, the wavelength is increasing. Wavelength is increasing, meaning lower energy, okay? Remember that. So increasing conjugation, increasing lambda max, and this is high energy, this is low energy, which means that if you have a conjugated system, then it absorbs at a lower energy. And that's the whole thing. Like, why is it doing that? Why is it, that the lambda max is changing and the epsilon is a little bit more complicated? Okay, so I'll try to do my best to explain that to you. And if you don't understand it, it's not even a big deal. The most important thing for you is, of course, conjugation, because that's what this chapter is about. Okay, it's conjugation. UV Viz is in the conjugation chapter, by the way. Okay, if you're looking in Klein, you will find it in the same chapter as Diels-Alder. And then this one, this is lycopene. Lycopene is found in tomatoes and carrots, so that's red in color. And so look at the conjugation in lycopene. Oh my God, every other bond, the whole molecule is conjugated here, and so it absorbs a little bit higher. So 470 is where it's absorbing. Remember, the visible region is 400 to 800. These are easy numbers to remember, okay, not very hard. So it absorbs at 470, so which means it is absorbing now in the visible region. Now, there is something specific about how you can predict whether a molecule is going to absorb in the red region or the violet region or the yellow region. We're not going to get into that, okay? That's a graduate course, okay? That why does it absorb in this region and not in that region, okay? Our thing right now is just to learn why it is even absorbing, okay? So you take a graduate course in order to figure that why it's absorbing in that particular region. Okay, so I'm going to take you back to MO theory. Okay, if you remember the MO theory that we talked about, I introduced this to you and I mentioned this to you, I think even with Diels-Alder and whatnot, conjugated systems, that there is the bonding orbital and there is the anti-bonding orbital. Okay, so let me remind that to you again. How that works is if you have hydrogen and you have one s1 electron in both of them, so these are called atomic orbitals. And then when you combine them together, they will form molecular orbitals. You combine two atomic orbitals to get two atomic orbitals will give you two molecular orbitals. The two molecular orbitals will go in absolutely the opposite directions. Okay, so one high energy, one really low energy. Where you find the electrons is, of course, low energy, and that is the bonding MO. Bonding MO. The top one, if you remember, I told you we put a star on that, and that's called the anti-bonding MO. Anti-bonding MO is usually empty because it's very high in energy. So electrons don't like to stay there. So this is the basis. This is the basis for UV vis spectroscopy, and that's what's kind of shown over here. So the other thing that I want to show you here now, because this is the basics. This is the basics. Once you have more molecular orbitals, then let me change the color and I'll show you what happens, okay, when you start getting more and more orbitals. The more orbitals will start fitting in the middle. So if this is the one, then there is going to be another one over here. And then if there is another one, then the other one will come here. And maybe there are two at that level, who knows? But it's kind of like a mirror image, if you remember, I told you. Okay, so whatever you have as bonding MOs, you're going to have the same mirror image as the anti-bonding MO. The main thing that is important here for UV vis, please note, okay, this is where you can start paying attention. If you were not, I know you were before. is these orbitals, the one that I'm going to highlight now. These two are the most important one. The highest one here and the lowest one on the other side of the line. So the highest one is called a HOMO, HOMO. Right here it says, okay, HOMO, which is the highest occupied molecular orbital. So HOMO, highest occupied molecular orbital. You will never look at HOMO the same way again, okay? Because I know we use that a lot in our general language, but you will never see it again. Every time you see a HOMO, you'll be like, oh, okay, this is the highest occupied molecular orbital. LUMO, which is the other one, on the other side, is the lowest unoccupied MO, molecular orbital. So the lowest unoccupied molecular orbital, and then there is the highest occupied molecular orbital. Let me know if you want me to stop anywhere, explain anything again, okay? All right. Now, between the HOMO and the LUMO, there is a line. That line is called the node. Remember that? I mentioned to you before. So right in the middle, okay, there is a line. You cross that line, you are into the antibondings now. Okay, that's kind of how it goes. That's why I drew that line, because that's the node. Okay, that's where the bonding and the antibonding separate. So what is UV-Vis? How does this actually work? So I told you in the instrument that you provide energy, okay, to the molecules. So you have a light source. I'm going to erase all of this because I may need to write something. Okay, so I explained to you that there is a light source, okay, in there somewhere. The light source is giving a very specific amount of energy. And what specific amount of energy is going to be in that range of ultraviolet and visible region. Okay, so between the 200 nanometers to 800 nanometers, whatever that frequency is, that's the light source that you have. In that light source, what happens is the electrons will start jumping. So you can see over here also, look at the HOMO and the LUMO, okay? So I'm going to show you this now. So here in the HOMO, you have 2 electrons. And in the LUMO, you have nothing because that is the antibonding. That is shown by the star, okay, on there. The star means it's antibonding. So what happens is when you provide energy to the molecule, electrons will start jumping from the HOMO to the LUMO. How much energy does it absorbs is what is going to give you your peak, okay, in the visible region. And that's it. That's the whole mystery there, okay? As to how you get that absorption is coming from what is called electron transition. When I talked to you before about the molecular orbital theory, I mentioned to you that molecular orbital theory is good for generally for photochemistry. Generally, we don't talk about MO theory, okay? We will talk more about hybridization. That's our theory. Lewis theory is our theory for bonding. The molecular orbital theory is not generally our theory that we learn first for any kind of bonding because its applications are limited, okay? We don't need MO theory all the time to explain anything. Hybridization, yes, we need that to explain a lot of the bonding, but MO theory we don't need to explain the bonding. The MO theory is used primarily in photochemistry because this is how you use it, okay? This slide is the classic example of how you would use MO theory because only in a molecular orbital theory will you be able to draw out all of these bonding and anti-bonding orbitals. Once you have the bonding and anti-bonding orbitals, molecular orbitals, then you can figure out these electron transitions. Where is the electron going from? Okay, it's going from the HOMO to the LUMO for sure. Okay, can it go from this part to that? Yeah, it can only when these two electrons have moved up here. So when both of these electrons have transitions up, now the HOMO and the LUMO has changed. So now things will start jumping in a little bit different way. So these are the jumps that the photochemist will look at in order to figure out all of these absorption properties and also the photo properties that molecules have, why they glow, why they behave in certain ways. A lot of molecules will change their properties with electricity, with energy, and that's the whole thing behind your phones also, right? All your phones, which are such beautiful colors, and we don't think about where the colors are coming from. These are actually all organic compounds, and they're just layers and layers of organic compounds on your phone would change colors with electricity. Okay, and so they're really critical. I mean, this whole part of molecular orbital theory, this is all very interesting in generating all of these kind of molecules, which change colors. So this is the theory behind this, okay, is that you have these HOMO and LUMOs, which means you have these transitions. Now, this amount of energy, will it change? Yes, of course it can change, okay, because right here, let me show you in this slide, and look at the numbers again. Okay, look at the numbers again. So if you have 2 double bonds, the absorption is at 217. But if you have 6 double bonds, the absorption is 364. What? This is low energy, right? That's what we said. This is low energy, this is high energy, which means that the HOMO and the LUMO for a diene is very far away, but the HOMO and the LUMO for this hexatriene thing, or the, I don't know, hexene, how do you even call that? I don't know, 6 double bonds. Let me just say it that way. 6 conjugated double bonds. The HOMO and the LUMO are much closer. So here, the HOMO and the LUMO may be this way, but here the HOMO and LUMO are very close. So the transition of the electrons is very easy to do. Okay, the energy required is very low. That's kind of what we're talking about here. Okay, and so that's given to us in this next slide. Okay, so the conjugation and the MOs. So the more conjugation you end up getting, the closer the orbitals start getting, and the change in the energy, or the energy absorbed by the molecule, gets smaller and smaller. Okay, so that's kind of how it works. So generally for me, the question for you will be, oh, here is a molecule like this, and here is a molecule like this. Which one do you think is going to absorb in a higher energy region or a lower energy region? So you just have to be careful when you read the question. Am I asking you for nanometers, or am I asking you for energy? Because if I'm asking you for nanometers, then this is going to be a higher nanometer, right? Because this is going to be the larger wavelength. But if I'm asking you for the energy, and let me go ahead and make this one to be isolated double bonds. So when I'm asking you for the energy, yeah, this is going to be higher energy. Okay, so it needs higher energy for transitions. So that's usually the kind of question I ask you. I'm not going to ask you to calculate epsilon for me. I already told you that. I'll have to give you data for that, and I don't want to do that. I just want you to understand and appreciate UV-Vis spectroscopy, okay, and how it works. So it's not super complicated, okay? At least at this level for you, I'm trying to keep it simple. Otherwise, it can actually get complicated, okay? And when you really get into photochemistry, it's just a whole other different world, and all you think about is, and all you dream about is HOMOs and LUMOs, that's all you think. It's not just the fact that any molecule absorbs energy, by the way, okay? So you have these transitions that happen, but the other aspect of photochemistry is actually the other thing also. How does these electron come down? So when they come down, so like if you give energy to something, it's kind of like you also, when you are feeling down and you're like low energy, you take an energy bar, or, and I hope you don't really drink those energy drinks. Those can be really, too much. But, you take some, chocolate, sugar, whatever, and you take that and you're like, okay, now I have energy. So now what do you do with that energy? Do you go clean your house? Do you study a little bit? Do you go out play basketball? What do you do with that energy? And that is your loss of energy, because now you're expending that energy. That is what I'm talking about with the green arrow, is that when the molecule starts losing that energy, how does it lose that energy? And that, let me just mention a couple words to you. Hopefully you can relate to them in some way. So one is called phosphorescence. And the other one, fluorescence. So phosphorescence is actually a very slow kind of jump down. So if there is an electron that actually jumped all the way here, one by one, they jumped up. Any electron that comes back by phosphorescence, they will come back in a stepwise manner. What does that mean, that they're coming back in a stepwise? It means they'll take one step, another step, another step. So they lose energy very slowly. That's called phosphorescence. And that is a property of a molecule. These would be the glow-in-the-dark toys. Okay, so they lose energy very slowly. And so if you give energy to a glow-in-the-dark toy, then, it takes them a while before they lose all their energy. And then it's, back again. You can energize it again, and then again, it will be all bright, So this is the cycle that's going on, okay, in the glow-in-the-dark toys. Phosphorescence, sorry, that was phosphorescent. Fluorescence is a little bit different. Fluorescence is generally when your light hits something, you give it energy, it glows, you take your light away, and it stops glowing. And these are most commonly the highway signs. Okay, so when you're driving on a highway, on a road, and you see those green signs, with the exits and all of that, when your light hits, you can see it much clearer, and that's fluorescence. Okay, so they glow in a little bit different way. That's not ordinary paint. They have to paint it in such a way that you can actually see at night. So, things are just a little bit different like that with phosphorescence and fluorescence and, photochemistry and all that. So this is, this literally is photochemistry, or this is UV-vis spectroscopy. So we went through the instrument already. And now you know about the HOMO and the LUMO and the theory behind it. So when you see a spectrum kind of like this, oh my God, what a mess I've made here. So when you see a spectrum like this, then you're like, oh, okay, I understand now what's going on, because I have certain orbitals that are absorbing at a high energy. Okay, so now if you had any absorption on this side, that's going to be a low energy absorption, but this one is a high energy absorption. Okay, and so that's kind of what you see, when you look at a UV spectrum. Okay, so here are some more absorptions given to you. So you can see that as the conjugation increases, here's the isolated ones, and look at the isolated ones. This is like really high energy because this is a low wavelength. And then as you keep coming down to the dienes and then more to the polyenes, look at the number, it's increasing. Okay, so the hexadiene is 227. The hexatriene is 257 or 258. When you do a graduate course, when you get into more of photochemistry, you can actually predict, okay, where your sample is going to absorb, because there are certain rules. If you remember that scientist we talked about a little bit, just a little bit, Hoffman. So Hoffman actually predicted a lot of these things, how you will see the double bonds and how these double bonds can change the absorption in ultraviolet and visible spectroscopy. Okay, so the more double bonds you have, then the higher the nanometers, the higher the wavelength, or the lower the energy. And again, why is it lower energy? Because the HOMO and the LUMO, they get closer and closer together. So there's not that much energy required for the electron transition. So here are some examples of some dyes, okay, and where their absorption is. So you can see methyl orange, which you use in titrations a lot. So methyl orange absorbs at 440. It's a nice reddish orangish kind of a dye. Indigo is the dye that you put in your genes, not that you do it yourself, but that's the dye that's actually you find in your genes. So without indigo, your genes will not be your genes. That's denim, right? So that's that color, indigo. And then Congo red, it's look at the size of this. The main thing I want to show you with these dyes is, okay, it's not the names of the dyes, it's actually the conjugation. Look at the conjugation in these dyes. You have so many double bonds going on, in all of these dyes. And so they absorb really well in the visible region. I really love colored compounds. I used to work with, I think I have it there. I used to work with porphyrins, and porphyrins are found in chlorophyll and hemoglobin. And, hemoglobin is red, and of course, chlorophyll is nice and green. And of course, all the fall colors, that's just degradation of the porphyrin happening, and you get all these colors. So here are some, of the absorptions that you see for a chlorophyll. You don't have to know any of this. The main thing is look at the conjugation in the molecule. It's a macromolecule, and look at how many double bonds you have in there, So that is visible spectroscopy. So I will open it up for questions right now. And I think that's it, really. There's not a whole lot going on. You don't have to predict whether something will be red or violet. The main thing about the red and violet, let me tell you what the red and violet is, since I do have that there. This is the red region. The red region is the low energy region, by the way. And the violet region is where ultraviolet is. So the violet region is going to be the high energy. And that's how you can remember it also. The red region is infrared. The violet region is the ultraviolet, towards the ultraviolet. Ultraviolet is higher in energy, okay? So that is how you can remember it if you want to. But that's it. That's all I have for visible spectroscopy. I know I went here and there a little bit. So let me pause here.